In terms of a bit more complex geometric sequence and arithmetic sequence type of problems, what you need to take care of is the information that is given. So here you are told that the common ratio, right? You were given the common ratio, or the common ratio is 1/3. So this is for a geometric sequence, isn't it? We have a geometric sequence and an arithmetic sequence that have the first term. So what I like to do, Mina, is this. I'll say this is for geometric. I'll say that I don't know what is the first term, the second term, and then the third term. I don't know that. Then this is for the arithmetic. I don't know what is the first term, I don't know the second term, and then I don't know the third term. Whenever I'm dealing with these type of problems, this is what I always do. And because they said a sequence, that's why I'm not putting plus there, plus. I'm just putting those semicolons because it's a sequence. Now we're given that they have the first term. So if I put A here and then A here, they are exactly going to be the same. Okay. Now the common ratio of the geometric is 1/3. What does that mean? Remember, this means that to get to the next term, we have to multiply by 1/3. That's what we were saying in previous lessons on geometric sequence, is that the ratio means the number you must multiply with to get to the next term. So that means I'm multiplying by this to get to the next term. The common difference of the arithmetic is 3. That means for arithmetic, if it is 3, that means I'm adding 3 to get to the next term. I'm adding 3 to get to the next term. So far I know that the second term here is going to be 1/3a, and then here I know it's going to be 1/3 squared a, because it's going to be 1/3 times 1/3. While this side I know it's going to be a plus 3, and then it's going to be a plus 6, because it's going to be a plus 3 plus 3. We just add the numbers, it's going to be a plus 6. Right. Then they say the sum of 22 terms of the arithmetic is 734 more than the sum to infinity of the geometric. This is beautiful. So you can see that the R value here for geometric is between 1 and -1, because it's a proper fraction. That means a sum to infinity exists. So if I were to calculate the sum to infinity here, I would say A1 minus R. Then when I substitute, A is going to be A, and then I'm going to have 1 minus 1/3. This is going to be the sum to infinity. So if I try to substitute further, it's going to be A2/3 there. Okay, so this is the sum to infinity for the what? For the geometric. Good. We found ourselves the sum to infinity for the geometric. I'm calculating it because they talked about it. And then they said the sum of 22 terms of the arithmetic. So if I were to calculate the sum of 22 terms for the arithmetic, I would say S of 22 is equals to 22 over 2. Remember, let me write the formula first, by the way. S of n is equals to n over 2, and then 2a plus n minus 1d. I'm using this one because they talked about the sum of an arithmetic. And then the sum of 22 terms is going to be 22 over 2. Then you're going to have 2a. I don't know the first term, by the way, but I know n is 22 because I'm adding 22 terms. I know the difference is 3. Right. Then what do I get there? 22 divided by 2, I think it should give us 11. Then you're going to have 2a. Now 22 minus 1 is 21. 21 times 3, I think that should be 63. Right. Yeah, should be 63. And then you have sum of 22. Right. So far this is the sum of 22 terms of the arithmetic. But how is this sum to infinity related to the sum of 22 terms there? That is the big question, to say, how do those relate? Let me just try to write this neatly. So how do they relate? Well, we're told that that sum of 22 is 734 times more than the sum of to infinity. So what that means mathematically, right? What that means mathematically is that So we are told that the sum of 22, it is 734 more. 734 more, not 734 times. We say 734 more. When they say more, it means you are adding. Okay, that means you are adding. So 734 more than the sum to infinity of the geometric. So that means it's sum to infinity plus 734, which is the same as this. Okay, if you want to write it in a more understandable way, you can say it is the sum to infinity plus 734, because it is 734 more. Okay, if it had said 734 times the sum to infinity, we would put multiply. But if they say more, you put plus. If they say less, you put minus. Okay, so that's what we have. Now we do have the expression for the sum of 22. Remember, we know that it is 11 into 2a plus 63, while this side is going to be a over 2 over 3 and then plus 734. This represents the sum to infinity, isn't it? While this represents the sum of 22 terms. Then you can see that the only variable we don't know there is a. If you have only one variable you don't know, that means you can calculate what you call, you can calculate that missing one. You don't need simultaneous. But if I had two variables that are unknown, I would need to use simultaneous equations. So I'm going to multiply by 11 so that I have 22a plus, now what is 63 times 11? So if we say 63 times 11, we get 693. So we write 693 there, and then now we have a over 2 over 3 plus 734. So here now it's just a bit of mathematics. But what I always tell people is that if you have a denominator, multiply both sides by the denominator, meaning multiply everything by the denominator. So I'm going to multiply everything by 2 over 3, and multiply by 2 over 3, and multiply by 2 over 3, and multiply by 2 over 3. Okay, multiply everything by 2 over 3. So if I do that now, I'm going to have 22 times 2 over 3, 22 times 2 over 3. I don't know if that is going to be correct. Can you maybe try to get the answer for me? So the answer is going to be 44 over 3. Thanks for that, A. And then 693 times 2 over 3, what do you get? So much. So you get 462, and then here this will cancel that. Okay, so we just be left with A. And then what will be 734 times 2 over 3? 1468 over 3. Okay, then for me it's just a matter of you solving for A. You can now say 44 over 3a minus the a, meaning I took the a that side. Then you can say the 1468 over 3 minus the 462. So guys, remember a and a are like terms. We just deal with the numbers. What is 44 over 3 minus 1? I think that should be 41 over 3. I think that should be 41 over 3. Then what about this side? Now what will be the answer here? So we get 82 over 3. So now what I can do here, guys, I'm just gonna multiply both sides by the denominator, multiply by 3 throughout. So now that 3 will cancel 3, I'm left with 41, and then a 3 cancels 3, I'm left with 82. Now if I divide by 41 both sides, that means that a is gonna be equal to 2. Okay, so I found the first term. Calculate the value of the first term. Oh, sorry, I didn't look at the question, but I just assumed that's what they want. That's what they wanted. Yeah, but you get A as 2, so you get your 5 marks. Not a difficult question, guys. I'm hoping that you get it. That it's just about the information you are giving. Go through step by step, filling in whatever you have. If you always do it like that, guys, there's no question that you won't get correct. Usually, I mean, this question, guys, for me personally, to be honest with you, I just took it out. I just take out a question, then we work on it. The thing is, the methods that I use, I know they will always get me the answer, because it's always the same thing every time. I think if now you've been following my method, that if I'm told I'm dealing with a geometric or arithmetic, I draw those things. I draw those dotted lines and say, I don't know the sequence. I'm just going to fill in whatever I have. And you will see, you will always get your answers. Okay. So now that that is out of the way, if you have a question on that, please do tell me. But otherwise, we can then now move to the business of today. We are starting with trigonometry. Okay, starting with trigonometry and then looking at a few things on trigonometry there. So in terms of trigonometry, remember, trig has a lot of parts. Okay, we have reduction formulas, right? We have reduction formulae, whereby we are dealing with 180 degrees plus or minus theta, 360 degrees plus or minus theta, 90 degrees plus or minus theta, right? So that is reduction formulae. And then we are also working with what? Special angles. It's working with special angles, right? Your 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 360 degrees, 270 also is there, but I'm just space, so those are our special angles. And then we have Cartesian plane type of problems, right, whereby we're either going to be having like cos theta is equals to a half, or we're gonna be dealing with cos theta is equals to m. Okay, right? And then after Cartesian plane type problems, we're gonna be dealing with compound and double angles. That is grade 12 now. Compound or double angles, right? Then you're gonna be dealing with identities. Then from there, after identities, you're gonna be dealing with general solution. And then after general solutions, you're gonna be dealing with 2D and 3D problems, which is also called solutions to triangles, and it's called like that in around grade 10 there or 11, right? Then the last thing, it's just that they're a bit of a lot, right? But then the last thing we're gonna be dealing with is gonna be trig functions. Now trig is plus or minus 45 marks in your end of year exam. In your paper 2. So it's almost a third of your paper 2. 1/3 of your paper 2. In fact, if you're mastering trig, you already passed the paper. Others are just to supplement. Actually, it's a very easy to pass paper 2. Master trig, master analytical, master stats, and then also try your best on Euclid. But it's also you are able to do it if you give yourself time. So these are all the things that are encompassed in trig. It's quite a lot, isn't it? So we're gonna spend some time today discussing reduction formulae along with special angles. but mostly we're just gonna focus on reduction formulae. Then the rest we're gonna cover them with other lessons to come. Right, so your reduction formulae, what is it all about, or what are we actually doing there? When we talk reduction formulae, we are referring to 180 degrees plus or minus theta, 360 degrees plus or minus theta, 90 degrees plus or minus theta. It's only 3 angles that we are using to reduce, right? These are your 3 reduction formulae. Obviously, because they will put plus or minus, we can say there are 6. But what is the whole purpose? Why are we reducing? Why is it called reduction formulae? Isn't it? So the whole purpose here is that you must understand type of angles. When you were around grade 7, grade 6, you must have learned about different type of angles. Can you remember some type of angles we have? So we have acute angles. What are acute angles? What would you say are acute angles? So true, acute angles are angles that are below 90 degrees. But can we actually say that mathematically? We can. Now what we do in trig, in analytical, in Euclid, is that if we do not know, like let's talk about algebra. In algebra, if I don't know a certain number, I call it x. Do you agree? If I don't know that what is the number, I call it x. But in trig, if I don't know the size of a certain angle, I use symbols. I can use theta, I can use beta, or I can use alpha. These 3 symbols are most common in trig. But not knowing an angle, you are not only limited to using these symbols. You are also allowed to use x, y, z, etc. to represent angles that you do not know. Now, speaking of which, when we say acute angles, I can represent them by doing this. This is a way I can use to represent acute angles. Someone might just say acute angles are angles that are between 0 degrees and 90 degrees, or you can also say acute angles are angles that are below 90 degrees, which is correct. Now mathematically you can write it in this way, to say it is an angle. I'm using theta because it could be any, but as long as it is an angle that is bigger than 0 degrees, that means here greater than, but then it must be less than what? 90 degrees. Those are acute angles. Okay, so the whole goal in there are also other type of angles, guys. We can name a few. Obtuse, right? Obtuse angles, which are between 90 degrees and what? And 180 degrees. Okay, those are your obtuse angles. Most probably I shouldn't be using these ones, these these brackets. Mathematically that would be a bit incorrect, so I'm just gonna use the proper brackets for that, which are these ones here. Okay, right, so obtuse angles, they are between 90 degrees and 180. Okay, so why are we not including 90? When you say an angle is 90 degrees straight, it's given a special name. We call it a right angle. Okay, so that's why they were not including 90 in any of these. Right, and then now, and then if an angle is 180 degrees straight, that's why I didn't include here. If it's 180 degrees straight, it's called a straight line. you're probably gonna have a straight line. So we don't have an angle. Well, the angle is 180, but it's causing us to have a straight line in a way. Then remember, there are other like reflex angles and the likes, but those are not really quite important. So the focus here is going to be on the acute angles, which are these angles that are between 0 degrees and 90. Okay, the whole idea behind using reduction formulae is because we want to reduce angles so that they are below 90 degrees. If you ask me why, I'm definitely gonna tell you that we are just doing it for the sake of fun, né? So that is your trick. Now, what is going to assist us for us to reduce these angles to angles that are below 90 degrees is what we call a cast diagram. Must have heard of a cast diagram. So this cast diagram is the one that we use to assist us in reducing the angles. Okay, so it would be going like this. Now let's dive deep into the cast diagram. Right, just right here real quick, the cast diagram. Right, your cast diagram is a way now of arranging these angles or looking at them graphically. So what we usually do is that we draw the diagram like this, and then as now we say, let's count our angles from this line to that line, because at the end of the day, what is an angle? An angle is a space between two lines. So that's why we count our angles anti-clockwise from this positive x-axis to that side again. Okay, then we say if we use a protractor, here it will be 0 degrees, and then here it's gonna be 90 degrees on this positive y-axis. This side you have a negative x-axis, and then that's where you're gonna have 180 degrees, and then here you're gonna have a negative y-axis whereby you're gonna have 270, because if you use a protractor and measure this angle here, it's exactly gonna be 270. Then when you make a full revolution, you're gonna find that that revolution is 360 degrees. Okay, right. Now that we have our diagram like this, it's important to know this diagram in exactly this format. Right. Now, any angle, good people, any angle that is going to be in this quadrant, right? We call it quadrant 1 here. So any angle that is going to be in this quadrant, which is quadrant 1, remember you got your quadrant 2 there, you got your quadrant 3, and then you got your quadrant 4. Any angle that will be in here, it's going to be in less than 90. While any angle that is going to be in here, it's going to be bigger than 90, but it will be less than 180. Any angle that will be here will be like that, right? Right. If you take your calculator, and put, let's start with, because remember, the ratios we're working with is sine, cos, and tan. So let's simply start with sine. Okay, let's start with sine theta. When we say sine theta, we are saying sine of an angle we don't know, or sine of any angle that we can think of, but we want to focus on angles that are between 0 and 90 degrees. Okay, meaning angles that are in the first quadrant in here. Okay, so if we take sine, let's just say remember theta can represent any angle, so let's just say you put sine 1 degree in your calculator. I want you to tell me the answer, but I don't want the exact answer. I just want the sign, right? Tell me if the answer is positive or if the answer is negative. That's all. Okay, just put sine 1 degree in your calculator. Tell me if the answer is positive or negative. So Mem is saying she found it as positive. We don't really care about what we get. Okay, can you try sine 6 degrees? Is the answer positive or negative? Great, positive. Now let's try sine 80 degrees. Positive or negative? let's go to sine 89 degrees. Positive or negative? We still get positive. Okay, let's try sine 91 degrees. Positive or negative? Yes, we get it as positive. Right, please bear with me, guys. We are going somewhere. Now let's put sine 150 degrees. Positive or negative? Remember, we don't really care about the digits on the answer. We just want to know, is it positive or negative? Positive. Great. Now we're almost there. Let's keep going. Say sine 179 degrees. Positive or negative? Great, we get the answer as positive. Now say sine 181 degrees. Positive or negative? Also put sine maybe 200 degrees, right? And then also put sine 269 degrees. Great, we get negative. Quite interesting. Okay, let's put sine 271 degrees, then put sine 300 degrees, and then put sine 359 degrees. Yeah, so if you do that, you should probably get all of them to be negative there. So what do you realize from this? This actually means that all angles that are between 0 degrees and 90, I want you to check all of the angles that are between 0 and 90 degrees. They gave our sign as positive. We got the sign as positive. So in this quadrant, we can say sign is positive. But in this quadrant here, right, in this quadrant, we also checked them. We checked 91, which is in here, right? Then we checked 150, which is also in there. Then we checked 179, which is also there, right? We checked all of them there, those that are between 90 and 180, right? Those that are between 90 and 180. We found that sign was also positive, right? And then in here, whereby they are between 180 and 270, it's like from 181 until 269 there, we found that in here sign was negative. And then also in here, that were between 270 and 360, which is 271 to 359. We know that like 270,5 is also there and stuff, but we're just saying between 270 and 360, we got our sine theta to be negative. So this means that sine is positive in this quadrant and that quadrant, but then it's negative in this quadrant and that quadrant. I hope that was clear. So that is why, good people, right, that is why our teachers told us that in here all of them are positive, because if you do a similar exercise with cos, you're gonna find that cos theta is positive for all angles that are between 0 and 90, but then cos is negative for angles that are between 90 and 180. You'll find that cos is going to be negative. And then in here, you're also going to find that your cos is going to be negative. But for some reason, you'll find that in here, your cos is going to be positive. In here, you're going to find your cos to be positive. But in here, you're going to find that it will be negative. That means if you put cos 181, it's going to be a negative answer. cos 269, it's going to be a negative answer. Cos 200, it's going to be a negative answer. So if you do that with cos, you will see that in here it's going to be positive. Between 90 and 180, it's going to be negative. Between 180 and 270, negative, and then like that. And then if you do a similar exercise with tan, you're going to find that in the first quadrant, tan is positive. In here, tan is negative. But in here, tan is positive. And in there is negative. Okay? So if you do a similar exercise with tan theta, this is what you're going to find. This is what you're going to find in there in terms of the answers. Okay? So, to then summarize whatever we are seeing here, since all of them are positive in here, we use the letter A to represent that all of them are positive in here. And then in here we use the letter S to represent that it's only sine theta which is positive in this quadrant. While here we use the letter T to represent that it's only tan theta which is positive, while in here it's only cos theta which is positive. And that's why we'll have your cast diagram. That's the origin there. So it's not just about all of them are positive in here, sine is positive. Why? You have to understand why. And for you to understand, we did that exercise. You saw it yourself. Now, another reason why this is true, that most probably you are not really told why, right? Or you are not told about, is the following, guys. Actually, this has a clear link with trig functions. I'm just gonna do the one for sine. If we were to draw a graph for sine theta, right? If we were to draw the mother graph for sine theta, that mother graph actually looks like this. Let me do this. That mother graph looks like this, whereby here it's 0 degrees, 90 degrees, I think is it 180. How is it like? Oh, okay, I mixed it. I'll just fix it now. Okay, let me fix it now. The 90 degrees, actually I think it's here. It's here, 90 degrees, and then here you have 180 degrees, and then here you're gonna have 270 degrees, and then here you're gonna have 360 degrees. Now I want you to check, right? And remember, here Akere is the y-axis, and then here is the x-axis. Remember, this side is positive y values, and then here it's negative y values. I want you to check something. I want you to check this part of the graph. Do you see that this part of the graph is above the x-axis? So all angles from 0 degrees to 180 degrees, from 0 to 180, your graph is above the x-axis. That's why we say your graph is positive. And then I want you to check here between 0 degrees and 180 degrees. Oh, my 180 is no more visible. Yeah, between 0 degrees and 180 degrees, do you see that sign is positive? That's because it's from 0 to 180. Then I want you to check something. I want you to check between 180 degrees and 360 degrees. The graph is below, isn't it? Let's use a nice different color there. Between 180 degrees and 360, the graph is below the x-axis, which means it's negative. Then I want you to check here 180 and 360. I want you to check how is sine. I want you to check how is sine. Do you see that sine is negative? Exactly. So these, whatever you are seeing on the cast diagram, comes from the mother graph of sine, comes from the mother graph of tan, comes from the mother graph of cos. You understand me? All of that comes from these. So whenever you are saying that you are getting a positive answer, it's because you are getting a positive y value for that particular x value. You understand? You are getting a negative y value for that particular, the angles you are putting in here, those are your x values. Those are your x values. And they are yielding or producing either positive y values or negative y values. And then that's how we come about with the cast diagram. So the most important thing is to remember that it might look minute But trust me guys, just an understanding of that is gonna then allow you to solve your problems, right? Now when we talk about 90 plus and 90 minus, right? Or rather, when you talk about now if you want to describe now the angles in the first quadrant, we then say in the first quadrant it is theta only, or you can say it is 90 degrees minus theta, or you can say it is 360 degrees plus theta. When you are using these things, you are referring to the first quadrant. While if you are referring to the second quadrant, you will be saying 90 degrees plus theta, or you will be saying 180 degrees minus theta. Then you'll be referring to this, right? And then for it not to then confuse us, I think we now know this, so I'm just gonna be removing these things and then leaving the symbols to tell the story. Okay, I'm gonna be leaving the symbols to tell the story, so that we have space now to talk about how do we describe the quadrant. So this is how we describe the quadrant, like this. Yo doesn't want to move, it's fine. Yeah, but that's how we describe them. And then if you're describing this quadrant, you say it is the quadrant of 180 degrees plus theta. It's 180, then you add a certain angle. Then this quadrant is going to be for 360 minus theta. But I want you to know that all the angles we are adding there, you see that theta, 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 all of those angles that we are adding, they are acute angles. When we say theta here, when we say angles that are in the first quadrant is theta, we are saying angles between 0 and 90 degrees are theta. That means theta is your acute angle. Is your acute angle. It's between 0 and 90. And that is why now when we say 180 minus theta, that angle would definitely be in here. Because if theta was not an acute angle, let's say you said 180 minus 100, you're gonna get 80 degrees, and that is going to fall in the first quadrant. It's no more going to be in the second. So it's important to understand that the theta here is an acute angle. It's also an acute angle, because when I say 180 plus theta, it's an angle that is in here. What if I say 180 plus 100? Do you see that I'm gonna have 280, and 280 degrees is in here because the angles that are in here are below 270. So you must understand that that theta, it is an acute angle, that theta we are adding there. That is why all of the angles we are going to see, we are trying to reduce them to be acute angles so that they are in the first quadrant. Okay, so just to summarize guys, cast the diagram, those C, A, S and T. I hope we now understand that the reason why we say all of them are positive is because if we put theta as any angle between 0 and 90, we get a positive answer. If we put sine of any angle between 90 and 180, we get a what? We get a positive answer. But if you put it like that, it's gonna be negative. If we put any angle bigger than 180, we're gonna get a negative answer. Then I think you also saw how it relates to the graph, mother graph. Then from there, you must understand that we're using 90 minus theta and the likes. We're referring to theta because theta is an acute angle. It's an angle between 0 and 90. That's our starting point. That is why the theta is usually called the reference point, the reference angle. So when you say 180 minus theta, you are reducing, where you are removing an acute angle so that you have any angle that will be in the second quadrant. If I say, for example, if I say 180 minus 70, I'm going to have 110. 110 degrees can be somewhere around here. This can be 110 degrees. If I say 180 minus 50, I'm going to have 130. 130 degrees might be something here. So this might be 130 degrees. You understand? If I'm removing there, all of the answer I'm gonna get is gonna land me straight in an angle that is in this quadrant, because that angle I'm gonna reduce is gonna be an acute angle. I hope that is clear. So then on our next session, we're gonna dive deep into how do we use that to solve problems, but just so that you can see, right? As an example, the reason why if you are getting sine 200 degrees, right, if you get sine 200 degrees, the first thing you'll have to do is to locate where is 200 degrees. Well, 200 degrees is an angle that is between what? It's bigger than 180, but it's smaller than 270. That means it's an angle that is in here, 200 degrees, right? 200 degrees. It's an angle that is there, isn't it? So that 200 degrees, since it is in this quadrant, it is in the quadrant of 180 plus. That means when I write the 200, I must ask myself what was added to 180 for it to be 200. What was added? It was 20 degrees. That is why we write sine 200 as 180 plus 20. We want to know what acute angle was added to get that big angle. Then once we know that we have sine 180 plus 200, let's remember that for the fact that it is in the third quadrant, the angles in the third quadrant for sine, they are negative. So that's why you put negative there, and then you just simply write sine 20 degrees. You just write sine of the acute angle. That is where now we're saying we are focusing on the acute angles, because you simply say sine of the acute angle, sine or cos of the acute angle, and the likes and the likes. So that's how you can reduce 200 to an acute angle. You simply, number one, locate the quadrant. By locating, you either check, is it 180 degrees plus or minus theta in that quadrant? Is it 360 degrees plus or minus theta? Or is it but 90 plus and 90 minus, we'll talk about them in another time, right? Focusing on this now for now. If right now I have cos 300 degrees, I can reduce it using the reduction formula. I just have to locate where is 300. Well, 300 is bigger than 270, but it is definitely smaller than 360. That's why I'm going to write my 200 degrees to say it is in the fourth quadrant. Since it is in the fourth quadrant, it is in the home of 360 minus theta. So I can write cos 300 as 360 degrees minus. But how much must I subtract to get 300? I must subtract 60 degrees. That is the acute angle I must subtract. Then my answer is simply going to be cos of that acute angle, which is what? Which is 60 degrees. But then I must decide whether the answer must be positive or negative. For it to be positive or negative, I look at which, the symbol in that quadrant. It's C, which means that cos is positive in there. That's why I'm going to put plus there. You get me? I hope this is becoming clear with people. If I have tan 225 degrees, I have to say, where is 225? Well, if I check my diagram, 225 is definitely bigger than 180, but it is smaller than 270. That means I should write tan 225 as tan, but it means it is in that quadrant. I must write it as 180 plus a certain angle to get 225. I must add 45 degrees. Then I say, okay, the answer then is going to be tan of the acute angle. Which one is the acute angle? Is the 45 degrees. But then is that going to be positive or negative? Well, that is the home for tan, because there is t in there. That means tan must be positive. Then that will be that means I reduced this to that. I reduced this to an acute angle. I reduce that to an acute angle. That's what we mean when we talk about reduction formula, guys. We are using these to reduce big angles to become acute angles. As simple as that. We are using that to reduce big angles to become acute angles. Why? We just love the acute angles. We don't really love the big angles. If I find myself having cos, let's just say 720 degrees, or maybe let's just say 390 degrees. I have to locate that and say, well, 390 degrees is bigger than 360, right? It's bigger than 360. That means you're talking about the first quadrant, 360 plus. That means I must write 390 as cos of 360 degrees plus a certain angle. I don't know what should be that angle. Well, I can add 30 degrees, then I'm gonna get 390. Then from there I can say cos of the acute angle. Which one is the acute angle? Is cos of 30 degrees. But should it be positive or negative? Well, in that quadrant, cos is positive because all of them are positive. So my answer will be positive cos 30 degrees. That's all I have for you today, guys. And then the next time, I'm going to show you now how to decrypt those big, large problems. That they are quite easy, guys. As long as you are able to understand this, then those ones will be quite easy.